So first of all, thank you very much for voting on my topics and allowing me to be today in front of you talking about OWL. Is it a solution or a problem? My name is Macq. I'm working in wireless industry since now 15 years, almost. And I'm currently working at Ruckus as Principal System Engineers. I hope you like French accent. You're going to get that from 30 minutes, so enjoy. Right. So security has always been a big thing on Wi-Fi. Since the day one in 1997, when it was first introduced, we got the web. Then we got WPA, WPA2, and WLPC. I won't go in details here. You have a lot of sessions yesterday and the day before about that. But the main point is, for all of those kind of Wi-Fi, there is a common point. All of them require to have the user of the device need a password, a certificate, a PS key, a SE, or whatsoever to be able to join the Wi-Fi. And so you need to get information before joining the Wi-Fi. Even for the open roaming we have here, as a European users, had to first go on the website, download the certificate to be able to go there. Now, if we want to provide a very simple Wi-Fi where anyone can easily access, we need to use open. And the reason why open Wi-Fi everywhere, in stadium, hotel, any place we need to provide an easy access, you're going to find an open Wi-Fi. Time to time, you're going to get a KPT portal on back to provide how to join the Wi-Fi from the KPT portals, but you, the device, will be able, and the user will be able to join the Wi-Fi very easily. So it's so convenient, and everybody is using that. So it's going to take a very long time before we go away from that kind of Wi-Fi to go to open roaming on other environment. The thing is, the issue is the security, of course, as everybody here knows. Because when you are in open and you set a link in between two devices, all the traffic, all the application will be unencrypted over the air. And so anyone in the middle will be able to hear what is going to happen, and that's something we want to prevent. To do so, there was an evolution in 2018 from the Wi-Fi Alliance. We introduced the enhanced open, relying on OWL. And that's what we're going to talk about today. So, what is OWL? First, it stands for Opportunistic Wireless Encryption. Second, you need to understand the difference in between OWL and enhanced open. OWL is defined by the IETF in the RFC 8110. Basically, it explains how it has to work. Enhanced open, it's different. It's a Wi-Fi Alliance certification program. So any device that need to use OWL go to the Wi-Fi Alliance certification band and get stamped compliant with OWL. So both are different, but you're going to see that for many vendors, OWE and enhanced open looks up some kind of synonym, and some will use OWL, some other will use enhanced open. Just consider both as synonym. Second point, OWE and WLPC. It is not the same. Everybody, or many persons on the internet think that OWL is part of WLPC or an extension or something. It is not. It is something different. It looks the same, but it is not. It's distinct. I mean, yes, it's about security. Yes, it was introduced at the same time. Yes, it used the same kind of method, but that's different. And today, it's easily possible to have device supporting OWL, but not supporting WLPC, and vice versa. So, OWL was first introduced by the IETF in 2017. Then the year after, we got the Wi-Fi Alliance certification program, enhanced open. And we had to wait 3 more years to get most of the devices supporting it. The last main milestone we're going to talk a bit about later on is a 6 gig, and that changed many things for OWL. First, what is the difference in between open and OWL? If you look at an association of a device, you will see the PRO request, you will see the PRO response, auth request, auth response, auth request, auth response, and at that moment, on open Wi-Fi, we are an unencrypted communication setup, and device can communicate. On OWL, it's a bit different. As you can see, we have, during the auth request and the auth response, we have a new key that's been exchanged between the device and the access point. And if we go in the frame, you'll be able to retrieve that exact key in clear in the communication. Those keys will be used to generate a PMK, and that PMK will be used to do the forward check and generate the different encryption key that you need to get an encrypted communication in between the access point and the device, like we have today with WLP2 or WLP3. So when customers see this kind of information, it might be a bit complex for them to understand why with just two public information we're able to communicate with encrypted data. And the explanation is here in the ECDH, elliptic curve Diffie-Hellman. So that's something that we might have to explain time to time to customers to make sure they understand what that means. And basically, everybody here knows it's something based on mathematical process where people are going to exchange key over the air. From these two keys, we will have a way to find a private key for both of them, which is going to become the encryption key. So that is quite simple to understand, but still a bit complex for someone not in technical part and who has not an engineering degree. So I found a much more easier way to explain that. Let's say we have two devices, an iPad and an access point, and in the middle we have someone trying to listen to what's going on. So it could be a hacker. First, both equipment will pick common colors, and the hacker in the between will be able to hear that colors. Second, both equipment will pick a secret colors, and they're going to mix these colors to get green on the left and orange on the right. Next step is we're going to exchange those colors over the years. And so for the hacker in the middle, it's going to be able to have the yellow, it's going to be able to have the orange and the green. And we should assume here that we cannot reverse the color composition. So of course, everybody knows that orange is going to be red and yellow. But let's say that from a mathematical perspective, it's impossible to identify which colors has been used for a mixed. So the hacker has no idea what was used. And next step, the device will apply again the privacy color, and at the end, they will all get the same one that's going to be used to encrypt the data over there. So it's going to become the PMK. If we talk a bit more about RWE, basically, it's like WLP2 and WLP3. You're going to require the RSN information element, and here the RWE AKM will be number 18. This also requires MFP protection, so management from protection has to be enabled when we do RWE. RWE also implements some PMK catching mechanism. So basically, when you are still on the access point, you move on those IPs, you want to come back, you will have a way to avoid to do again the forward check. And that is done through the PMK ID that's generated during the first connection to the access point. And then when the AP will come, with the device will come back to the APs, it will be able to skip that part. It's like when you go to the building, you will see the guardian in front of the door. It's going to check your papers first time, and then it will take a picture of you. And next time, do is just a picture, it will be able to let you allow without checking your identity anymore. So we do have PMK caching, but we don't have fast roaming or anything such like that with RWE. There was some draft at some point, but no one, it expired by now, and looks like there is no more work on that. Last point, just to be sure, RWE cannot authenticate users, right? It's like an open Wi-Fi. Its goal is to allow everyone to join the Wi-Fi, but encrypt the data over there. So there is no authentication. Who support RWE? So here I did a quick table, and you will be able to retrieve that in my slides. But basically, if you are on Apple, you need to have iOS 16 or 16.1 for iPad and macOS 13. And here you have the list of all the hardware compliant today with RWE. To be able to work with RWE, you require to have the software and the hardware. It's not just one of the others. It's both at the same time. When you are on Android, you're going to require Android 10 or later. And for Windows, it's going to be Windows 10, version 10 May 2020 or above. Here again, you need to also have a hardware compliant with RWE. I won't be able here to list all the equipment, obviously, but you got the point. If your hardware is not compliant, your device won't be able to join an OWE environment. So we are in the middle of a phase where we have devices compliant with OWE, some are not compliant, and how should we proceed? Because if we look at what the IETF first mentioned, the idea was to create two Wi-Fi, one in open, one in OWE, and then people picked the good one. The issue is that devices are not able to see if a Wi-Fi is in OWE or in open, and if it picks the wrong one, it's going to get a mistake, an error, so that solution is not a good one. The other one proposed by the Wi-Fi Alliance, which was mentioned yesterday, is the OWE transition mode, which basically rely on two Wi-Fi. The first one is opened, and the second one will be hidden on the back in OWE. Both are tied by some information and will indicate the position of the other device. And so when the device is compliant with support OWE, it will be able to reach the hidden Wi-Fi in OWE. The other equipment will be able to join the open Wi-Fi. So if we look in more details, basically the two Wi-Fi will be tied by information element contained to the probe request and the beacon. Sorry, the probe response and the beacon. Both work on the same band, and so you're going to have the same into the 4 and 5 gigs, and you're going to have this Wi-Fi tied this way. So it's not a duplication. We're going to see a bit after that. It's possible to have the two Wi-Fi on different band, but in most cases, it is the case. We have the two Wi-Fi on the same band. One quick point here, you will see a lot of time -OWE-TR on my OWE Wi-Fi. It's because it's a way on Ruckus. When you create a Wi-Fi in open transition mode, it's going to add on the initial name this at the end. So the reason why you're going to see a lot of -OWE-TR at the end of the Wi-Fi name. It's mandatory that both Wi-Fi share the same policies to have the exact same experience. And it's just a requirement, a suggestion that broadcast and multicast should be shared across the two Wi-Fi. So we say that this element of information are present in the beacon and the probe request. All this looks like. So it's something done by the Wi-Fi Alliance. So it's going to be vendor-specific information, 221. Of course, it's going to be linked to the Wi-Fi Alliance. And the subtype 28 indicates to the device that it's going to be information about OWE transition mode. And just below, you'll find the BSSID and the Wi-Fi, the ESSID, sorry, of the hidden OWE on the back. So it's also possible to have an open one in 2.4 and a hidden one in 5 gigs. If we do so, so it's very specific first. You won't find that a lot, and I don't really see the point to do that, but still it's possible. And if you do so, you're going to have two additional and optional fields. The band info and the channel info will act as some kind of map information for the device to be able to retrieve the OWE Wi-Fi hidden or somewhere else on a different band and a different channel. Of course, those two optional fields has to be set together. You can use just one and not the other one. Both come together. Now, if we take a device, an iPhone, my iPhone, that's what I did here to understand exactly what's going on when I click on the OWE transition mode environment. You're going to have this. First, ask the device to join the OWE transition mode Wi-Fi here. And so my device is going to send a probe request for that specific Wi-Fi. The access point is going to reply to my probe request on the same Wi-Fi. But at the same time, it's going to include this specific information element we just mentioned, letting the device know that there is another Wi-Fi on the back. And so my device will then send a new probe request to the new Wi-Fi. So it just switched thanks to the probe response from the access point. And then we have the usual probe request, authentication phase, association phase, and the forward check. at the end, the device is connected to the Wi-Fi. It's connected to the -OW-TR Wi-Fi. But from a user perspective, we don't show that to avoid any confusion. And so the user will think that it's connected to the initial Wi-Fi he requested. But in the back, the system used the OW mode to get something more secured. So it's interesting to have a view on how a device show information, because from a user's experience, it could change a few things. There is some recommendation done by the IETF that we should avoid to use a lock icon next to the Wi-Fi that are in OW to look like an open one. So in Apple, we don't have the lock. In Windows, the same, we don't have the lock. And in Android, well, we don't have the lock anywhere. And the Wi-Fi Alliance also defined the fact that we just mentioned, if we go in OW transition mode, we should always show the open Wi-Fi when the device is connected, even if it's using the OW one, as I just mentioned a bit before. Now, if you look at what Apple display, when OW was first introduced in iOS 16, when people was connected, they got no locks and they got no error message, security warning about the fact that you are in open Wi-Fi. So it works as expected. Since iOS 6.17 and also iOS 18, the security message comes back. And I have to say I not fully agree with that, since in the message we can see that this is unsecured because it's no security. Okay, there's no authentication, why not? But there is no, the data is exposed over the network, which is not over the air since it's encrypted. We report that to Apple, and we hope we're going to get an explanation or maybe a quick change to remove that message or change it a bit. On macOS, we have the same kind of information. It's going to mention that the network is unsecured, and from a security perspective, it's going to mention it's none, despite the fact that we are here in 6 gigs, and of course, open mode doesn't exist in 6 gigs. On Android, it's a bit different. We're going to get information about the type of encryption. Sorry, just to come back here. So basically, there is no way today on Apple to see if we are audibly or not once you join the network. On Android, you're going to be able, in the security section, when you click on more information for your Wi-Fi, you're going to be able to see that you are in enhanced open. And if you are in open Wi-Fi, it's going to be mentioned none here. On Windows, you will have, for some device, the possibility to show you that audibly is not supported. And you're going to get this kind of cross just in front of the Wi-Fi symbol to let you know that you shouldn't try to use that one. But if it's supported, you're going to get, I hope your French is good, you're going to have a message saying the type of security is OW. So as I mentioned at the beginning, enhanced open, OW as 2 words used kind of the same way by the different vendors. Now, the question could be, what's going to happen if you have a Wi-Fi in open-OW? So the name of the Wi-Fi is open-OW, but on the left, it's in OW, and on the right, it's open. And I want to move the device from the two. What's going to happen? So first, why do I want to do such things? It could be done because for a specific reason, you have to mix legacy APs with new APs, and you want to enjoy the OW on the latest one, or it could be because you want to migrate from open to OW, and then you're going to change the settings, and it will be like moving from the right to the left. So I made several tests on my labs, and what I figured out is that if you are on iOS, you won't be able to move from OW to non-OW. You're going to get a message, and you will have to first forget the Wi-Fi to be able to join the non-OW one. But if you move from non-OW to OW, it will work just fine. On macOS, you're going to have in both cases a message letting you that something changed, and you have to manually approve the fact that you want to move in between the two. On Windows, it won't work either. When you're going to leave the access point on the left and go on the right, it won't authenticate on the new access point. You have to click again, and it will create a second profile on your environment. And for Android, it just works. All right, so let's talk a bit about 6 gigs. 6 gigs change a lot of things. Many people in 2.4 and 5 could ignore OWE because it's different. It's something you don't know exactly what it is, and so partners, customers didn't implement that. But now with 6 you cannot ignore it anymore. And so you have to play with OWE because open won't work in 6. If I take back my previous diagram, I can see that I won't have any. I won't have anything in 6 since open can be broadcasted in 6 GHz. So I will have to manually add a Wi-Fi in OWE with the same name on 6 GHz. Some vendors can do that automatically. So when you set up, configure an open Wi-Fi, it's going to automatically create an OWE1 in 6 GHz. Some others don't. But it will require some action. It might require some action from you to get the Wi-Fi in that 6 GHz. Now, if we continue the test I made in the past, and if we try to move from AP1, where we're on 3 radio, to AP2, where we're in 2 radio, it could happen a lot of time because now that we have 3 radio, which is a bit more expensive than 2 radio access point, some people might want to choose 3 radio for high-density environment and 2 radio for the other place in the building. So when I first join AP number 1, all the devices, of course, all those devices support 6 GHz, will join the 6 GHz OWE WLAN automatically. Then when I move from AP1 to AP2 from iOS, it's not going to work. And the device will remain stuck on the access point number 1. And if you are too far from AP1, you're just going to lose connectivity. It will never join AP2. For macOS, it works just fine for Android too. And then from AP2 to AP1, it's going to work for the iOS. It's going to come back in 6 GHz. It's going to work for the macOS too. And for Android, it's going to remain stuck on 5 GHz. And to move it back in 6, you have to disable, re-enable the radio of the Wi-Fi card interface on your device. And then it's going to go back in the right place. Last example, if we go in transition mode, then we will have, again, all devices joining in 6 GHz, but then it's going to work just fine for iOS, and it's going to roam on the OWE Wi-Fi on AP2, so the hidden one from the transition mode. It's going to roam just fine for the macOS and for Android, and then again, it's going to work just fine. So that's probably the best settings configuration you want to do if you want to mix. Just be aware that time to time on iOS and Android, the device didn't come back on 6 when it come back in AP number 1, but stay on 5. It was some kind of random. For the macOS, I never had an issue, and it always came back in 6 GHz. Now, if we talk a bit about Wi-Fi 7, Wi-Fi 7 also a new challenge for OWE. So in Wi-Fi 7, one of the main features is MLO. So many people talked about MLO during the previous day. And the thing is, with MLO, is that you have to share the same AKM across all the radio. So you have to have the same type of encryption across the 3 bands. If you want to use 6 GHz, you will have to have OWE or WLPC. But since today we're talking about OWE, basically you will have to set up all your network, all the Wi-Fi in OWE. And if you do so, you will go back in the initial issue where you have to create 2 different Wi-Fi, one in open, one in OWE for 2.4 and 5, which won't be perfect. Meaning that today, MLO is quite complex to set up in production with OWE. So, the conclusion, I know I should start with that, but here we are. Clearly, OWE is a solution on something. It's clearly solving all the problems we have from a security perspective with a guest Wi-Fi. It makes sure that your data will be secured over there, so no one will be able to read it, no one will be able to change it. And also, thanks to the MFP, you're going to be able to be protected against some DDoS attacks that are quite a kind of common on other environments. At the same time, you have some new problem. It generates some complexity because we have no wording, no word that vendors are going to use. They're going to mix it. You're going also to see that the implementation process is a bit more tough complex. And depending on the vendors for the Wi-Fi infrastructure, you're going to have more or less tasks to do, and the way to do it is a bit different. So it's add more tasks, add more job, and it decreases a bit the complexity. Also, it's not supported by all the devices, I have mentioned. But on that point, it's not that bad, since we have the transition orderly mechanism, which works pretty fine. It's a better solution than the one that we have today with WLP2, WLP3, which mix the same on the same SSID. Here we have two distinct SSID, and that makes the job very fine. But it required an extra Wi-Fi, and we don't like such things. We don't like adding Wi-Fi because it's not good from a RF optimization. And it also requires more configuration if your system is not able to generate a second one automatically. And so more configuration means more potential mistakes and more bad experience for the customers. Also, mixing open and audibly, as we saw, it might be an issue time to time. And especially since the behavior of the device might be different. But we saw that there is specific configuration we can set, and they're going to provide a good way to work, and the device will be able to roam in between the different access points when we have a mix in between 6 and 6 GHz with audibly and open in 2.4. Last problem for audibly is the integration of new solutions such as MLO that won't work fine today because it will require audibly in the 3 bands. If you look at most of the problem comes from the integration and the mix of open and audibly. And what you have to keep in mind is that, like for web, like for WLP, at some point, open and audibly tier will disappear, will go away from the landscape, and we will know this period as a transition period N, where we can stop using open and audibly. At that time, audibly will be just fine and perfect solution. Easy to set up, secured, more secure than the open one, at least encrypting the data over the air, and it's going to be able to use the latest technology, latest features, so that will be perfect. The thing is, when are we going to reach that specific time? Well, it will depend. Some sites are still using web. Some sites are still using WPA. So it's a bit complex to let you know when you're going to be able to remove open and transition mode. But the thing is, for sure, it will depend on the verticals, the solution, the customers, and you have today great analytics tools. So I invite you to use it. Check the trend. See how many devices supporting audibly, how many still stuck on the open one, and that will help you to take a decision to when you should remove the open and transition mode, and hopefully it's going to happen ASAP. That being said, thank you very much for listening to me, and I wish you a great day.